Welcome back, everyone. We're going to be solving LeetCode 104, maximum depth of a binary tree. So given the root of a binary tree, we want to return its maximum depth. They define a binary tree's maximum depth to be the number of nodes along the longest path from the root node down to the farthest leaf node. So given example 1, we should return 3, right? There's 1, 2, 3 levels to this tree. So whenever you see or hear levels, you should automatically think breadth first search, right? Breadth first search traverses a tree by level, and it's generally, I like it better than depth first search, so it's generally my go-to for tree problems. So that's what I'm going to use today. So we'll say from collections, we will import dq. We will say our q is going to be equal to dq of root. And I'll show you two different ways to do this problem, but for right now, we're going to use breadth first search in a queue. All right, so we've got our queue. We put the root on our queue. So now what do we have to do? Now we have to loop through and grab all these elements. So how are we going to do that? We are going to say while we're also going to have a resulting array. And what we're going to do is we will grab these elements or these nodes by their level, and we will append each level to our resulting array, right? So 3 will be its own level because 3 is the root. That's the only one at that level. Then we'll grab 9 and 20. So we will have 9 and 20. And then on the last level, we have 15 and 7. So we'll have 15 and 7, and then at the end we can just return the length of this resulting array, right? There's 1, 2, 3 levels in here. Pretty easy, right? So that's the first way I'm going to show you. So let's do that first. We'll say while the length of our queue is not equal to 0, what do we want to do? We want to define a level to be equal to an empty array. And we want to loop through all of the nodes inside of our queue. We want to say for I in range length of our, whatever the length of our queue is. We want to grab the node from the front of the queue. So we'll say node is going to be equal to queue dot pop left. And then we have to make sure that the node is non-null. We can do that by saying if node is not none. What will we do? We will take the value of our node, put it into our level, and then check to see if this node has any left and right children. If it does, we will put them on our queue. So let's do that. We'll say if node is not null, we want to say level.append node.val. And then we will check if node.left is not none. We will add it to our queue, append node.left. We'll do the same thing for the right. Node.right. Okay, so once this block finishes, we're done with the level, right? This entire block. So what do we have to do? We have to exit the for loop, and then we'll have to say if the length of our level that we just appended all those nodes to, if that is not equal to 0, we will want to append it to our resulting array. So we can say res.append level. And then at the end, like I said at the start of this video, we can just return the length of our resulting array, which should give us the answer. So we'll say run. Okay, we passed both test cases. We'll submit. Perfect. Okay, so the time and space complexity of this is going to be the space complexity is going to be bound by the length of the queue plus the length of our resulting array. Now, the time complexity is going to be O of n, right? We're touching all of our nodes at most one time. And then we have to say we're also doing this for loop on the inside of our while loop, so we're also doing another O of n inside of an O of n. So you could say it is O of n, where n is the number of nodes in the tree, times by however many nodes we have to touch at each level. So in that case, we could say it's O of n times k, where n is the number of nodes in our tree, times the number of nodes at each level. Okay, so what's a better way to do this? A better way to do this is to still use a queue, but we don't have to use a resulting array. And instead of a resulting array, we'll say our maximum level will be equal to an integer. We'll start it at 0, and this will keep track of the depth of our tree. So every time we go down a level, we'll increase this maximum level variable by 1, and then we can just return this at the end. But to do that, we are going to, instead of appending just the root, right, we don't have to only append the root. We can structure this data however we see fit. So what I'm going to do is append the root along with its current level, which happens to be 1. And I'll do this as a tuple. So now we can loop through our tree, again using breadth first search. We'll say while the length of our queue is not equal to 0, we will say our node and the current level we are at is going to be equal to queue.popLeft. And then we will say if our node is not none, we want to potentially update our maximum level. So we'll say if the level is greater than our maximum level so far, we can say maximum level will now be equal to our current level. Okay, now we need to check to see if the node has any left and right children. If it does, we need to put them on the queue along with their level. So now we can say if node.left is not none, we will say queue.append as a tuple node.left along with the current level plus 1. So we'll say level plus 1. We'll do the exact same for the right side, is not none, queue.append a tuple of node.right and level plus 1. Okay, now at the end, we should just be able to return the maximum level we have so far. Make sure I spell everything right. Maximum level. So let's run this. Okay, it does run. We'll submit. Perfect. So the space complexity now is only going to be bound to the length of our queue, and the time complexity, well, let's write this, we'll say queue.length. And then the time complexity is going to be O of n, right? We're only touching each node at most one time within our while loop. So the time complexity is going to be O of n, where n is the number of nodes. And that'll do it for LeetCode 104.